Some of you have successfully absorbed what the mathematical proofs are out of that course. Some of you might not, even though you have taken that course. So here's a rule I'd like to go by. When you prove something, each step, don't think that some statement you have in mind and then try to prove it. It's very difficult for me to follow your thought. So just like I did before, you go through some calculation on your own, however disorganized, doesn't matter, and then you write down the clear statement. This is a conclusion of my thought process. This set is equal to that set. And then you separate the clean, non-confusing statement and try to prove it very clean fashion in whatever is accepted as a proof. So first thing you have to do, not just the entire problem, this is what I want to prove. Each step, you make some progress towards something. If that's stated clearly like this, it really helps the reader, right? So this purpose in here is both for you and myself, the reader, to clearly understand what the thought process is. And the second thing is that you can write down in the next step with this, using this implication symbol, correct statement. Then it's correct because two correct facts are listed. But you have to go through some sort of reasoning. If your reasoning uses something the level of above calculus 1, using the fundamental theorem calculus 1 or higher, you better list it briefly. This is reasoning. And some of the reasonings are very specific to that situation, and then you have to write out more. And all that, and you will see if, do I have to write down all these things, the kind of feeling that you eventually feel? So I'd like to put it this way. When you do this rigorous reasoning, you have to give me some indication that you thought about something and you feel that this is worth mentioning something. So it requires a lot of self-examination. Once these things are right, and it's really easy to skip the correct thinking and just write down, it follows this and that. So I can't really go down to that intimate level of your thinking process. So I will definitely leave some part to you. You have to thought through and write down some clue that gives me that, hey, this person thought this process is worth mentioning, wrote down something. So I have definitely some idea about what you went through. And another thing is that you can't use big gun to prove a little thing. Maybe that big machine gun is actually based on whatever you want to prove. So you have to understand that kind of chaining. Sometimes this theorem has nothing to do with that simple statement, then you can use it. So a good example is proving this fact, x approaches 0. Do you know what happened to this limit, sine x divided by x, as x approaches 0? The answer to this one is 1. One way to calculate this is using the L'Hopital's rule. Who remembers L'Hopital's rule? Benjamin. Right, derivative here is a cosine. Derivative down there is 1. So the quotient is not quotient rule, it's L'Hopital's rule. And plug in x equals 0, then it becomes 1, right? But that's a way to calculate it, but it's not a way to prove it. Because this is a fundamental fact in the differential calculus. Almost every trigonometric fact about the differential calculus is based on this fact. And L'Hopital, taking the derivative and everything, they're all based on this fact. So if you use L'Hopital's rule to prove this fact, that's not a proof. But that will be a correct calculation. So when you prove it, you have to understand this type of chain of reasoning. And then you can imagine that's hard. How do you know all this fact and what's underneath it? At least if you're covering this section, and at least that amount you can probably handle. Or you have to question yourself, and going back to where? Your self-examination, if you have to think about what you are doing is kind of okay or not. So next thing I prepared here is this fundamental facts. So I'm going to call F1. This is some serious business in mathematics. These are fundamental facts. Sometimes they're called axioms. Have you heard about axioms? It's this smallest set of principles that you don't have to prove, but we play with that logically to get at other statements. So suppose we have lots of fundamental statements here, F1 and F2. That makes sense? This is some statement about integers. This is some statement about real numbers, something like that. okay, in the bottom of the chain of the mathematical reasoning. And by combining these two things, what do I mean by combining these two things? Logic, right? Using the pure logic, you get a one statement. Does that make sense? So if you open up the calculus book, they give you this definition and definition and definition. Using the logic, playing with this definition and that definition, you come up with intermediate value theorem. Right? These are the kind of definitions, and these are theorems, right? And then you can imagine web of these things. You can't even, number this one with these integers anymore. So there are some set of fundamental statement is given. You don't have to prove this. This is given because it's self-evident. It's quite obvious. Two parallel lines never meet each other. That kind of statement. Have we kind of sense of that? And then you get this statement. So it's to explain visualize what I mean by chain of reasoning, right? Okay, you can't, for example, if the statement T1 is relying on S2 and T1 is relying on S1, and you can't prove S1 using T1, that would be a circular argument. That's what I was talking about here. All right? So here's some statement. It's really puzzling. It's supposed to be puzzling here. This is a big result in modern mathematics. Maybe there is some, as tilde, is a statement. It's a very simple statement about numbers. And think about it as a possibility that this is what we have as an axiom. We have, let's say, 10 or 20 axioms in mathematics. You do whatever you want to logically develop the statement, whatever that comes out of this one, right? Isn't that possible sometimes? There is a statement you just innocently written down. It cannot be reached by this web of logic. Can you imagine that kind of statement? Right? Let's go and kind of put down the condition. It's a set. It's a set of a statement. Here, it cannot be reached under the developing the logic out of this 10, 20, whatever the fundamental statement is given. And it's a Gödel, mathematician. It's the same contemporary of Albert Einstein. He came up with that statement, which is proving this fundamental statement they given, 5 or 3 of them, is not contradicting to each other. That's a statement about this fundamental statement. Suppose you have F1 and F2, F3. You have to logically add and subtract whatever the logical thing you do. The following statement cannot be reached under that kind of operation. And what was that again? This fundamental statement F1, F2, F3, for example, are not contradicting to each other. Can we prove that? That statement cannot be proven using this fundamental statement, right? So this is called the limit of reasoning. You can't prove everything, right? There's certainly the limit of reasoning, and we have to understand that. But we have to do our best to clarify the chain of reasoning and things like that. And if it is not that particular statement, if I have something called S star, something called Riemann hypothesis, have you heard about the Riemann hypothesis? It's an unproven statement yet. And I'm questioning, what if the Riemann hypothesis is outside the realm of the axiom system we have? You will never be able to prove that statement, right? So that this type of nonsense nobody cared about, but it became very fashionable by that time. It's gone, it's coming back again because of some genius mathematicians beginning to work on this problem. So you see this problem showing up, and again, you might see it recently, sooner or later, some news media talk about this Hilbert problem again, its limits of reasoning. It's called a decidability problem. All right, so I have to mention that whenever we talk about this proof things. Spend 30 minutes. But this is the main idea. You can't use your failure as a proof. Sometimes because you see certain thing is obvious, it can't happen. How on earth can this happen? Therefore, shouldn't happen. That's not a proof. That you feel like it is impossible, it is not really a proof. So you have to go about it in a different way. Okay? So I copied it down here, and that's reality. That's what really happened. Whenever you're in that situation, how am I going to write this one down? This obviously can't happen. And then here's the technique. In mathematics, it's not physics, and in mathematics, we describe a certain thing. To describe number one is tricky, right? So it is the bottom of our chain. You have to go back to your elementary school and see how your teacher introduced number one. It is that fundamental, right? So other things, we usually put down this condition. Think about the set we describe. If it is not sequential set, we put down two conditions to describe a membership, right? And we try to turn into sequences. So the conditions are important thing. So again, we often use this condition to describe existence of things in mathematics. It's not tangible thing in the physical world. It is all happening in our mind. We use this condition. If these conditions collide each other, contradict each other, then our conclusion is that element doesn't exist in mathematics. Makes sense, right? You write down condition 1 and condition 2, condition 3, you realize that they're contradicting to each other, then you conclude that there's no such element. So that's what we're going to end up at using it. Right? Anybody remember about this incompleteness theorem, that we have this fundamental statement in mathematics sitting in the bottom of the chain of reasoning, right? And we want to establish that these guys are not contradicting each other, right? Could we prove it? Gödel showed that there's no way to prove that fundamental part. So it's incomplete in our, the logic is actually incomplete in there, all right? But as long as we have that one given, rest of the part shouldn't contradict each other. That's the thing. So it was second quiz problem, was it not? Right? And then, but I didn't select that. So let me phrase it this way. S is a non-empty set. I don't know if you paid attention to this non-empty part, but it is important. And you will see how it kicks in our argument. Non-empty subset of Z, right? Okay. And it satisfies certain conditions. There is this fixed M. This is important, but you may write down, or you will have this note. Fixed M is fixed, right? What is changing is this X. Maybe S has infinitely many elements, maybe not. We're going to go through all of them. All of them, it doesn't go below M, right? There's a statement like this. This is a phrase that is bounded below. Do you remember that part? Bounded below? That's what that is. All the elements is bounded by some element to the left-hand side. And then it says S contains the smallest element. All right? And if you think about it, and how sparse these integers are on the real line, it's kind of obvious statement. That's why we take it as a principle. But I will use this as an example to use this contradiction thing. Introduce the proof by contradiction. I think it's the most natural thing to do. All right? What you have to look at in this proof is that how we actually break things down and clearly understand what reasoning we're using, not relying on, hey, this part's obvious, no need to write down this obvious things. That's not the point of it. It's just, point is introducing the proof by contradiction. So here is, this doesn't have to be the part of the proof, but this diagram really explains the idea behind this proof by contradiction. So this is very difficult to think of. Right now, the sets that I introduced so far are all, the elements are numbers, right? But this one here is elements. This is a huge set whose members are sets again, right? Usually, for that kind of thing, we use curly brace. What does that curly thing represent? It's a set of sets. Okay? So I have one set S1 in there. That's a member. Member is not a number. Member is what? Member is a subset of Z. And another number, S2. Okay? There are lots of sets, subset, but they're all bounded below by what number? Fixed number M. Okay? So this curly C is a collection of all subset, especially non-empty subsets, right? Non-empty subsets such that it's bounded below by M. Any question about what is just being written here? C is a set, right? What are the members of this set? Subsets of Z. These are the members of the set. For example, it can be written like this, 1, 2. Does it look like a subset of Z? That's a member. The subsets makes it another set. It's pretty crazy. But that's, this is called object that satisfied the collection of all the objects that satisfy this given condition. Is that right? I want you to read that condition. Some arbitrary set, we don't know how it looks. Only thing we know is it's not empty, bounded below. And what did I do in C here? I defined it. Think about every subset that satisfies this condition. That's one thing we're looking at. And the second condition is that smallest element. All right? So I'm going to draw another collection. Does it look like a curly D? It's my curly D. This is a collection of all the sets. T's in there. T1 and T2 and T3. They have, T's have no smallest element. What did I just do? That's not a statement we have, right? Statement we have is that this set has a smallest element, right? But I just negated that. Here's why. In the statement, we have this property, bounded below property. You're not going to negate that, right? That's a given property. We want to test if they have a smallest element or not, right? So for that, we negated that. We're going to consider opposites. Like we have this all possible sets that we have it here that satisfy a condition. Now we're going to consider all the sets doesn't have a smallest element. And what about this intersection point? What do you think? That's what we're interested in. What is our prediction? Which fall in here? Set that's bounded below and has no smallest element. This statement suggests that there's no such set. If you've bounded below, they all have smallest element, right? But we just said that, okay, we have all the bounded set here, but we consider all the sets that there's no smallest element. If there's intersection in here, that will violate this principle. Your goal is that there's nothing there, right? How do you show a certain thing doesn't exist? You show certain conditions contradict each other. That's what we're going to do. All right? So we pick that element. In that, there is that S0. S0 is from where? Intersection of curly C and intersection of a curly D. Set of all sets that is bounded below and does not have a smallest element. Right? Then the first step is the following. We're going to choose an element. How can you choose an element inside S0? What condition do we use to be able to choose an element? S0 is from C, so there are 3 conditions in C, right? Or 2 conditions? Really 2 conditions in C. What are those 2 conditions in C? Curly C. Non-empty, bounded below, right? Those are the 2 conditions that determines that curly C. Non-empty allows you to choose an element, right? So can I just pick an element x1 in that S0? Can we do that? Why can you do that? Non-empty, there is something in there. You pull it out, right? Okay. Then there is this group of mathematicians, very small group of mathematicians, want to make sure, absolutely make sure, when you do something in mathematics, it has to be clear and precise. So they're asking, which one are you picking? I know there's non-empty. Just give me a specific, precise, non-ambiguous description of which one you're choosing. And then there's no way to do that. There's no way to give a precise description unless you use this principle that we're about to prove. So it's a circular argument, right? So it stops there. That is called axiom of choice. Don't ask how I'm choosing it. If you're non-empty, there's something in there, pull your hands in there, pull one out. No more question. What is that called? Axiom of choice. You can choose it. If it's non-empty, you can choose it. So there is one thing that was in there. And let's use the fact that it came from D. What do you know about D? If it came from D, you know it's not the smallest element, right? So is it clear that there will be x2 in that S0 such that x2 is smaller than x1? Is that right? There must be a smaller element. There is no smallest element, right? Is that correct? All right. So I'm going to ask you to do this in a set 1 homework problem, not writing down everything, just saying this. It takes time, but I'm explaining things here, okay? I'm trying to focus on that. So how about what's the next step? We got x2. What are you going to do? x3, right? What's x3 and what's the reasoning? Can somebody volunteer? So does that allow us to choose one more element than x3? Is that correct? Yeah. How about next element? Do we have x4? Because of the same reasoning, right? What does that do? Does that define infinite sequence? Yeah, because you keep getting smaller. We've seen that if you keep smaller and smaller, you have infinitely many distinct elements. So we have what? We have a what kind of sequence? Unbounded infinite sequence, right? So let's do one more. How they're spaced is very important. Because they're integers, you're using some axiom about the principle of integers. What relationship do you know about between x1 and x2 rather than is it smaller? Like less than or equal to. Can you come up with less than or equal to kind of information? It's obvious less than or equal to. Can I push it further down one more? Is that true? x1 and x2 are integers, and x2 is smaller. If you subtract x1, 1 from x1, isn't that one step closer, but is never below x2, right? Because they're at worst they're one apart each other. Is that okay? Does that feel like it's something we can obtain from a principle of a axiom about integers? Yeah. So we rely on some axiom about integers. If they're integers, they're only one apart at worst each other. So if you subtract 1, what worst can be? Either is equal to x2, or still x2 is further to the left. Make sense? So what do you expect about the relationship between x3 and x1 then? Isn't that right? You're just 2 steps ahead. At least you guaranteed. If you subtract 2, x1 is not going to be below x3 because of what we have there. So how do we describe all this thing nicely? This is your conclusion, right? So xn in general is going to be less than what? What's the number that you have to put it in there? See, if you look at this relationship between the index we have in the left-hand side of the inequality and number is subtracting from 1 less, right? So what would be that number here? N minus 1? So it's supposed to be proved. How do you prove such a thing? What technique do you use to prove this thing? I just put a dot, 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 right? Just explained it, right? Mathematical induction? Sounds about right? So this is where you use mathematical induction. There's an observation and try to clearly state right there. There's a clear statement, right? And you try to prove it using induction. All right. Then it's going to violate, eventually what it's going to violate? It's just keep going smaller and smaller, right? xn. It's keep pushing it down. It's going to be a problem with m, don't you think? M is there. Everything should be above this m. Okay. So what do you think that we have to choose this m nicely? Choose n wisely so that what do you want to accomplish? xn is less than what number? Sorry about that. Any volunteer? We want contradiction, right? You go below m, which is intuitively correct, right? keep going down by at least moving one step ahead. All right? So would that be a contradiction? Why would that be a contradiction? Xn is still where? All this x1 is still coming from S0, the set that we put these two conditions, right? Bounded below and no smallest elements, right? So S0 there, and you can see it went below there, but that's the property we have. Does it look like a contradiction? There's an element inside S0, but it go below an M. That's not the bounded below condition. So we pull out contradiction there, right? Good? Contradiction. So what could be this choice of M then? And then it's a violation, it's a contradiction. And you go back to this principle earlier there. If you stated that several conditions and you realize that they're contradicting to each other, then the conclusion is that there's no such element, right? Yeah. So I figured out what could be the good choice of M here. And I think I concluded that is x1 plus absolute value of x1 plus m minus 1 or something like that. All right? But I didn't show why this one works. I'm going to leave this one to you. And think about my choice of this x1 plus absolute value of x1. What is he doing with that number? So first you plug in those m in place of n there and see if you can conclude this inequality xn less than m. Less than or equal to m, I think. All right? Still violates, right? Does this make sense, the plan? Okay, so with that choice, we're going to pull out a contradiction, and then we're going to go back and think about this part here. Is there any set in this zone here? What do you say? We pull out arbitrary S0 here, and we show that it's contradicting, so there's nothing in that overlapping zone, right? So only that you can pull out in here, none of them belongs to that area D. What is D? No smallest element. So it's outside, this means it has a smallest element, right? So this is the most concrete description of a proof by contradiction. Why is it concrete? Because I described it in terms of sets, not in terms of logic, which could be weird, and if you describe it by contradiction. Okay? Yes? Typo, this is supposed to be our choice of n, right? Yeah. Here, this is a general description of relationship between xn and x1, right? And then we're going to choose this n wisely such that we pull out this contradictory statement. That choice of n is x1 plus absolute value of x1 plus m minus 1. If you have a better description, go ahead and try it. But this is my suggestion. All right? But you still need to explain why this one works. In the proof, you don't have to share that how you discover this one, right? Just the validity of the argument is correct. But when you do this with me, and if you share how your clever thinking was described briefly, that really helps me but to write down mathematical proof, you don't have to write down everything that you discovered. You only write down what you discovered is correct. Good? This gives us different way of interpreting. So that's my only example we're going to go about proof by contradiction. All right? So let me give you a little summary here. So I'm going to call that one C again. What was that C? It's a kind of collection of condition. The curly C was a set, right? It was a collection of everything that satisfied the condition that is given. In the earlier statement, our object is not a number, it happened to be sets. So we have to think about sets of sets. But it could be numbers. So what is the C again? Set of everything that satisfied whatever the 5 or 6 conditions they gave. And we want to conclude if D was the opposite thing, this condition. So I'm going to call E. Does it look like curly E? Right. So that's the statement. We want to see everything, condition C implies condition E. You understand meaning it implies, right? Logically it implies. So different way to see that is that this is, in terms of condition that implies, but this is a set, everything that satisfies condition C, and this is everything that satisfies condition E, whatever that stated there. And this is equivalently that this is simply subset relation. Everything that satisfies the given condition sits inside everything that satisfies the concluding the condition. All right? So in that way, it's a concrete description, the imply, right? So what this suggests is sometimes you don't have to logically derive these things. You just, if you're able to calculate everything, if you calculate C, if you can calculate E, and just show that C is sitting inside E, and that also accepted as C implies E. All right? So let me give you this weird example. X cubed plus y cubed equals 1, and where x and y are q. What are those? Rational numbers, right? Yeah. This implies x to the fifth plus y to the fifth equals 1. And they are both in rational numbers. Okay? And I'm claiming there's no way algebraically you can deduce this one. All right? There's no way to do that. No one succeeded that. But if you look at all the possibilities of rational numbers that satisfy this condition, it turns out 1, 0, and 0, 1 is it. That's the only one. It's a famous Fermat's last theorem. That's the only possibility. Then that's what is the entire possibility that satisfies this first condition is these two things, right? And what is the second condition? It's also Fermat's last theorem that says this is it. That's the only rational number satisfy these two conditions. This condition. So as a set, they're the same thing, right? So if x cubed plus y cubed equals 1, does that mean x to the fifth plus y to the fifth equals 1? Answer is yes. The only possibility is 1 and 0 and 1, and it is always true. So this is a weird implication. There's no logically derive and manipulate to get to the fifth power, but the possibility suggests that it is the case. We're going to include this type of thing as an implication. So if possible, go through the possibility and shows that the possibility shows up. That's one way to show something. But usually imply suggests that you manipulate to get to that stage. All right.